Okay, today we're going to look at square root functions. Functions that have a square root symbol in them somewhere. They're all based on the parent function, which is y equals the square root of x. Alright, so this would be a series of ordered pairs where each y coordinate is the square root of each x coordinate. You can find the points on this by simply plugging in points and connecting them to create a graph. So for instance, I have picked a couple of points here to plug in, 0, 1, and 4. If you plug in 0 into x, you get y is equal to the square root of 0, which is of course 0. If you plug in 1, you get y is equal to the square root of 1, which is of course 1, so 1, 1 would be the next ordered pair. And if you plug in 4, you would get y is equal to the square root of 4, which square root of 4 is 2, so the ordered pair would be 2. And you can see here each y coordinate is the square root of the x coordinate. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. So we have a couple of ordered pairs that we can put onto our graph. So we have 0, 0, we have 1, 1, and we have 4, 2. We can see that the graph kind of looks like this. That if we connected these points, the graph would look something like this. And we can assume that it keeps going over like this. So this is the parent function for the square root. Alright. Now you'll notice that it doesn't have any negative values. Okay, there's no x values that are negative because you can't take the square root of a negative number. That would be imaginary. And we can't graph imaginary numbers on this coordinate plane. So we would say that the domain is any number greater than 0. So that would be all the numbers from 0 to infinity, including 0, so we use a bracket there to show that 0 is included. The range, well, we can see that also our y values are not negative either, because you take the square root of a number, it's not going to be a negative. So our range is also 0 to infinity. And a bracket on 0 because 0 is included. So this is the parent function. All square root functions are going to be some transformation of this parent function. Okay, it may be shifted over here, it may be shifted down over here, it may be shifted up, it might even be stretched out a little bit, but they're all going to look like this same basic function. It might even be reflected, maybe it's going this way. Alright, so all of the functions that we talk about today are going to be some transformation of this function. Now, how do we tell what the transformation is? Well, it all goes back to basic transformations. The transformation is standard form, which is y is equal to a square root of x minus h plus k, where the h and k are the initial points, which would kind of be like a vertex a little bit, but it's the initial point, it's where it starts. And that's because those are the vertical and horizontal shifts. Okay, so the h is the horizontal shift, the k is the vertical shift, and since we're shifting the point 0, 0, which is the starting point on the parent function, whatever the shift is just becomes the new starting point. Okay, so these give you your starting point, hk, that's your initial point. Keep in mind this always opens to the right if the x under the radical is a positive. Okay, so if that x is a negative, it's going to open towards the left because that's a reflection. Alright, so let's take a look at this. Let me see. Are we supposed to graph this? Yeah, okay. So let's take a look at this. We want to graph this. Now take a look back at this for a second. The domain, we can determine what the domain is by setting the radicand greater than 0, greater than or equal to 0, and solving for x. Okay, so this is the radicand. This is going to tell me what the domain is. I just need to set this x minus 2 greater than or equal to 0 and solve that for x. But we will very easily be able to tell what the domain is just by looking at the graph. Okay, so let's start. Our standard form is y equals a x minus h plus k. Alright, so the h and the k are our starting points. Our starting point is going to be our h is 2, minus 2, so minus h is 2, k is 5, so our starting point is going to be 2, 5, 2 comma 5. Alright, let's pick another point, 3. So we'll plug in 3. So instead of x minus 2, it becomes 3 minus 2, which is 1. So we got square root of 1 plus 5. Square root of 1 is just 1, so it's 5 plus 1, which is 6. Okay, so when you plug in 3, you get 6. So 3 comma 6 will be our next point. And then we'll plug in 6. So we'll plug in 6, so we get the square root of 6 minus 2, which is 4, plus 5. And the square root of 4 is 2, so we get 2 plus 5, which is 7. Alright. Alright, so let's take a look at what this looks like. So our first ordered pair is 2 comma 5, right here. And that's our initial point. That's where it starts. Next ordered pair is 3 comma 6, so it's right here. Our next ordered pair is 6 comma 7, so 6 comma 7 is right here. You notice that it looks just like the other function. It just looks like the parent function, except it's been moved a little bit. Alright, we can see the domain is everything to the right of 2. So instead of it being 0 to infinity, it's now 2 to infinity. So the domain is 2 to infinity, including 2, of course, because there's a point there. The range, well, the range used to be 0 to infinity, but it no longer starts at 0. On the y-axis, the graph starts at 5, so it's from 5 to infinity. So 5 comma infinity is our range. And you can see that these come directly from the transformations 2 and 5. Okay, so the h gives you the new domain, the k gives you the lower boundary for the new range. Okay, the h gives you the lower boundary for the new domain, the k gives you the lower boundary for the new range. And that's our graph. Now, of course, it doesn't go over here. There's nothing over there. Alright, now let's look at this one. This one's a little bit more difficult because it has a negative 2 out front. So let's see what that negative 2 is going to do to this. The starting point is, of course, negative 3 and negative 1. Okay, x minus h. So in order for this to be x plus 3, h would have to be negative 3, and k is negative 1. Alright, let's plug in negative 2 next. So negative 2. So negative 2 plus 3, that is 1, so square root of 1. So negative 2 times the square root of 1 minus 1. Square root of 1 is 1, so negative 2 times 1 is negative 2, minus 1 is negative 3. Alright, and let's plug in 1. You'll notice that we're plugging in values that will turn the radical into a perfect square. Okay, when I plug in negative 3, it turns the radical into a 0. When I plug in negative 2, it turns the radical into a 1. And when I plug in 1, it turns the radical into a 4, which the square root of 4 is 2. So this is, if I plug in 1, square root of 4 is 2, so I got negative 2 times 2 minus 1. So it's negative 4 minus 1, which is negative 5. Alright, so let's see what this one looks like. The starting point is, of course, -3, -1. Whoops, that's -3, +1. -3, -1, right here. -2, -3. And 1, -5. Okay, so remember, -3, -1 was the starting point, so this was the starting point. So it looks like this. Alright, well, a couple of things to notice about this square root function, okay, because this thing changed it drastically. The -2 out front changed it quite a bit. Not only did it flip it over, okay, because typically ours were over here and now it's flipped over, not only did it reflect it across the x-axis, it also stretched it out a little bit, okay, because we're used to seeing it look like this, and now it's like this. So this a value actually has two transformations. The fact that it's negative, which causes a reflection, and the fact that it's not 1, in all the problems before it was 1, now it's 2, which causes it to stretch out a bit. Alright, now the domain is going to be a little bit different here because the lower bound, there is no lower bound on this one because it's been flipped over. There's only an upper bound. Sorry, that's not the domain, I'm talking about the range. The domain, there is still a lower bound here, okay, because the range, it starts at -3. Sorry, I keep saying range and domain. Let's start with the domain. Let me start over. The domain. The domain is the x-axis, okay, so we can see that the lowest coordinate on the x-axis is -3, and it moves to the right of -3. So the domain is from -3 to infinity. The range, there is no lowest point because the arrow is pointing down. So if the arrow is pointing down, the lower boundary is -infinity because it's just going down. But it does have an upper bound on the y-axis, okay? Because if you follow the graph upwards, the highest point is -1. So -1 is the upper boundary. So the range is from -infinity to -1, including -1. Alright. Once again, we have an a value that is a little bit different. It's 1/2. Alright, we can still ascertain the starting point because it's just h comma k, so it's 5 comma 3. And next we want to plug in x values, specifically x values that will turn the radical into a perfect square. So 5 minus 5 is 0. The next one we would pick is 6 because 6 minus 5 is 1, which would give us the square root of 1, which is just 1. So this becomes 1. So you got 1/2 times 1 plus 3, or 1/2 plus 3, which is 3.5 or 3.5. And next we pick 9 because 9 minus 5 is 4. So 9 minus 5 is 4 and the square root of 4 is 2. So you got 1/2 times 2 plus 3. So 1/2 times 2 is 1. Let me actually write this out so that everybody can see what I'm doing here. Okay, what I'm doing is I'm plugging in 9. 9 minus 5. Plugging in 9 for x. Okay, so that would be 9 minus 5, which is 4. And square root of 4 is 2, so it's 1/2 times 2 plus 3. Half of 2 is 1, 1 plus 3 is 4. So the next ordered pair would be 9 comma 4. Alright, so let's graph all of these. We got 5 comma 3. It's our starting point. 6 comma 3.5. So 6, 3.5 is right here. And then 9, which is off our chart, it's like right here, comma 4, that's going to be like right here. Don't have to be exact, we just need to be somewhere near it. Okay, so something like that. Alright, this 1/2 doesn't look like it did a whole lot. What it did is actually crushed it. Okay, instead of stretching it out so that it goes like this, it crushed it down. It shrunk it. Alright, so the domain here, well, the lower boundary for the domain is 5, and then it does not have an upper boundary, so this goes from 5 to infinity. The range, which is the y-axis, the lower bound is 3, and it doesn't have an upper bound, so this is from 3 to infinity. I think this is the last one. Yes. So we got our last example here. This one is a little bit different, mainly because it's not written in the proper form. Okay, so the problem with this is that the k value is at the beginning, so it looks a little bit confusing. The way that this should be written is negative square root of x plus 4, and then that 2 should be at the end. Okay, now this makes a little bit more sense for us to look at. We can see that the starting point is negative 4 comma 2. Alright, so we're going to pick some values that will give us perfect squares in the radical. So negative 3 would give us 1. So we'll plug in negative 3 into the x. Negative 3 plus 4 is 1. The square root of 1 is 1, so we got negative 1 plus 2, which is 1. And then we'll plug in 0 into the x because 0 plus 4 is 4, and 4 is a perfect square. So plug in 0. 0 plus 4 is 4. Square root of 4 is 2. Negative 2 plus 2 is 0. Okay, so we got all our points. Let's go ahead and graph these. Negative 4, 2. Negative 3, 1. And 0, 0. This was our starting point. Okay, so something like this. And once again, we can see what this negative sign has done is it's reflected it upside down. Okay, it's flipped it over upside down. So our domain, the lower boundary on the domain is negative 4, because that's the lowest x value, and it goes to infinity. And for the range actually has an upper boundary, not a lower boundary, because the arrow is pointing down, so there is no lower boundary. But the upper boundary on the range is right here at 2. And those are our square root functions. Alright, in the homework, page 81, 3, 4, and 6, page 82, 3, 4, 3, 5, 2, 3, and 5.